Greetings and welcome to an introduction to parts per thousand, PPT, which is a method we're going to use in Chem 221, Chem 222, and or Chem 223 to measure precision. And precision is how close your measurements are to each other. So parts per thousand is really useful to scientists. Perhaps you've found 2 molar mass values or 2 heat capacities for metals, or perhaps 2 values of K, the rate constant, or 3 or 4. You wouldn't use it for just one, but you can use it for 2 or more. So without further ado, let's see how this works. Parts per thousand, which again is going to be abbreviated PPT, is a way that chemists often use to measure the precision of your measurements. So again, you have to have 2 or more measurements, but then you can apply this parts per thousand, and it's a pretty cool thing. Parts per thousand, the name is a little confusing. Parts per thousand can be used as a measure of concentration. So for example, a parts per thousand that is a concentration would be 1 gram of solute in 1,000 grams of solvent, something like that. But this is a different type of parts per thousand we're going to be using in Chem 221, Chem 222, and Chem 223, or at least with me, your instructor. Our parts per thousand will be a measure of precision, how close your measurements are to each other. And it's a pretty simple thing to do, and you get a number which the magnitude shows you how close or, for example, far away you are. Parts per thousand can be known in the math world as a relative standard deviation, and the important thing for us is that it can be applied to any set of data where you have more than just one experimental value. So maybe you calculated a wavelength for a certain experiment, and you have 2 values ever from 2 separate experiments. This would be a good time to apply parts per thousand. Or perhaps you measured the percent potassium chlorate in a mixture, and you have 3 values. Parts per thousand could be applied. When you're done with the parts per thousand, you will end up with a unitless number. So again, you can start with percentages or wavelengths or molar masses, anything, but at the end, parts per thousand is just a number, a unitless number. And the smaller the number, the greater the precision. So if you have a really small number, i.e. a number under 30 parts per thousand, for example, wow, pat yourself on the back, you did a great job, your equipment is awesome, you're paid attention to the experimental parts and stuff like that, really awesome. On the other hand, if you have a larger parts per thousand, it doesn't mean that you're a bad scientist, okay? It might mean that your experimental procedure, the equipment you used, or maybe the actual methodology itself was flawed. And this happens in science, all right? It doesn't always happen perfect the first time, that's for sure. So a parts per thousand, small or large, will tell you something. Ideally, we'd like small parts per thousand, but again, if our equipment maybe hasn't been calibrated correctly, or perhaps our technique isn't as good, or maybe the actual methodology itself hasn't been found to be perfect, all of these would be reasons why you might have a high parts per thousand. So to calculate a parts per thousand, it's basically a 3 or 4 step process. And I'm going to go through the steps right now with just some generic X1, X2, and X3. So these X values could be molar masses, they could be percentages, they could be temperatures, who knows? But whatever they are, this is the process you'd want to go through. So if you wish to find a parts per thousand for your 3 values, X1, X2, and X3, you would start off by first finding the average of your values. And to find the average of these values, you'd add them up or take the sum of them and then divide by the number of values you have. So in this case, you'd add up X1 plus X2 plus X3 and divide all of it by 3. The second step of your parts per thousand process would be to find what's called the deviation of your values. And the deviation is the absolute value difference between the average number you just calculated and your individual values. Now, it's important to remember that these will always be positive numbers. You'll never have a negative deviation. So for the first one, you would take the absolute value of the difference between the average number that you calculated minus X1. And deviation number 2 would be the absolute value of the average minus X2, and the third one would be the absolute value of the average minus X3. You now have an equal number of deviations to the number of values you have. So we started with 3 values, X1, X2, and X3. We're now going to have 3 deviations, and we can call it deviation 1, 2, and 3. You want to find the average of these deviations, and it's the same process you used for the average earlier. You're just going to add your 3 deviations together and divide divide by 3. So deviation 1 plus deviation 2 plus deviation 3, and all of that divided by 3. And remember that your deviations should be positive numbers. If any of them are negative, turn them into positive. That's what an absolute value means. And finally, to find the parts per thousand, you take the average deviation number, you divide it by the average, and you multiply by 1,000. So again, whatever units your average value was, grams per mole, wavelengths, temperatures, whatever, your average deviations will be the same. So you end up with a unitless number, and the smaller the parts per thousand number, the better. Now, if that was about as clear as mud, which I understand, let's go through a couple of examples and see how you would find parts per thousand for these sets of data. So the first example we're going to look through is we have 3 percentages, 35.72%, 35.92%, and 36.02%. Let's find the parts per thousand for these values. This could be examples of percentages from the unknown chloride lab, or for a percent potassium chlorate lab. I mean, anything is possible, but it doesn't really matter. We just want to find a parts per thousand for them. So the first thing you want to do is you want to find the average of your percentages. So you want to add up those three numbers, those 3 percentages, and divide by 3. In this case, it comes out to be 35.89%. And notice how 35.89 is between those 3 numbers. That's a good thing just to double check. Once in a while, I've seen students forget to divide by 3, for example. So you want to make sure that your average makes sense based on the numbers you have, and it is kind of right in the middle, so that sounds about right. Next thing you want to find is the deviation. And again, the deviation is the absolute value of the difference between your average and the individual values. So if you look at those, we're taking the average, 35.89, and essentially subtracting each of the individual values. So 35.89 minus 35.72, that comes out to be 0.17%, which is fantastic. But notice the next one, 35.89 minus 35.92. Initially, that would come out as minus 0.03%. But absolute value, which is what those up and down lines mean, absolute value means make it positive. So again, I can't highlight this enough. All your deviations should be positive numbers. So deviation 2 will be positive 0.03, and deviation 3 will also be positive, even though it looks like it'll be negative at first, positive 0.13%. Once you have your deviations, you want to find the average of the deviations. So you're going to add up those 3 deviation numbers and divide by 3. It comes out to be 0.11%, which again looks about equal and stuff there for those different values. And then finally, parts per thousand will be the average deviation divided by average times 1,000. So we'll take 0.11%, divide by 35.89%, multiply by 1,000. This parts per thousand comes out to be 3.1. Usually parts per thousand under 30 are considered to be really good, so 3.1 would be a really good parts per thousand. Those 3 values are all very close to each other. They're all very close to about 36%. If you'd round up to 2 sig figs, that's really good. So again, smaller parts per thousand is what we strive for, but again, it may not always be possible. So if you do get a higher parts per thousand, don't lose any sleep about it. Here's another example. We have 2 values this time that are molar masses, 36.92 grams per mole and 39.10 grams per mole, and we want to find the parts per thousand. So these values could have come from, say, the molar mass of a volatile liquid lab or the freezing point lab. Hard to say, but we have 2 numbers and we can find the parts per thousand from them. So like before, you want to first find the average of your numbers. So add up 36.92 plus 39.10, divide by 2, you get 38.01. That looks reasonable. You're kind of halfway between the 36 and the 39 number, so that seems reasonable. Next, you want to find the deviation, which is the positive difference between your average and the individual values. So again, you can see how I've set it up there. It looks like the first number, 36.92 minus 38.01, would be negative, but you always want to make it positive, 1.09. And the second one, 39.10 minus 38.01, will be positive by default, no problem. Now, the reason I'm doing this example is I wanted to show you if you only have 2 values and you're finding the parts per thousand, the deviations should be the same number or very, very close. Within sig figs, they should be. So in these problems, you can see they're both 1.09. And that kind of makes sense because the average is the halfway point between the two values, so the deviations will be the same. This is a nice way to check yourself when you're doing problems, finding the parts per thousand and you only have two values. The average deviation should equal the same number because, again, it is the same number. 1.09 plus 1.09 divided by 2 gives you 1.09, no problem. And then finally, the parts per thousand will be the average deviation divided by the average times 1,000. So 1.09 divided by 38.01 times 1,000. In this case, you get a parts per thousand of 28.7. Smaller parts per thousand are always better. This is larger than the last example, but it's still fine and stuff, no problem. And again, sometimes you can have parts per thousand much higher, and it's just a function of the type of experiment you're doing, the equipment, maybe the methodology, stuff like that, no problem. One final example, I'd like to give you a hint. If you have 3 or more values that you're finding parts per thousand and you want to get the lowest parts per thousand value possible, sometimes you can kick out the outlier to find a better parts per thousand value. So let's look at an example here. We have 4 numbers, 2.62, 3.16, 3.05, and 3.02. And probably just visually looking at them, you can tell that 2.62 doesn't fit as well with the other data. The other ones are between 3.02 and 3.16, but 2.62 is definitely an outlier. It doesn't fall in that data range. Well, if you use all 4 values, and I'll let you do this on your own to make sure you can do it, you'll find that the average is 2.96, the average deviation is 0.17, and your parts per thousand is 57. And that's not a horrible parts per thousand, but maybe you could do better, all right? So in this case, because you have 3 or more, you can kick out the outlier, the one value which is farther out from the other 2. So let's kick out 2.62 and refine the average. So if we kick out 2.62 and we want to find the parts per thousand for only 3.16, 3.05, and 3.02, you can go through the steps, and I encourage you to do this on your own. You'll find that the average value is 3.08, the average deviation 0.057, and wow, your parts per thousand dropped to 19. So you do get a better parts per thousand when 2.62 was omitted when you kick it out, all right? And again, that 2.62 value, who knows why it's an outlier? Maybe you weren't paying attention, or maybe the equipment was weird on that time and kind of spazzed. There's a gazillion different reasons, and don't take it personally, all right? But if you have more than 2 values, you can kick one of the values out to get better parts per thousand, and you are absolutely justified in doing that. If you ever have questions on this, if you want to do it to your data, you're welcome to ask me. I'm happy to help you with it. Reach out to me, and that's cool. The Learning Success Center / Avid Center would do it. If you only have 2 values that you want to find parts per thousand, then you're stuck. You can't use this kick out the outlier idea. But if you have 3 or more values, heck yeah, kick the lowest one out, get better parts per thousand, feel like a cool scientist. Okay, that's it. Good luck with your lab. Again, if you have questions on anything, reach out to me. I'm happy to help. You can also talk to the Learning Success Center / Avid Center. They will help you out as well. All right, good luck with your lab and have a great day.